Alrighty, mathematicians, we are now on to section 5.2, sigma notation and limits of finite sums. So before we talk about finite sums, we need to talk about how we can write finite sums. So sigma notation allows us to write sums of terms in a compact form, right? So we have this sigma, and we have k equals 1 on the bottom and on the top, and I have this a of k right in front of it. And what that means is I can write a1 plus a2 plus a3 plus ... all the way up to an. So notice that k starts at 1 right here. We start at 1 and we move up one integer. So I'm going to 1 to 2 to 3. If I start at 4, I'm going 4, 5, 6. There's no half or whatever. So we define the index of the summation k, and it tells us where to start. So the number on the bottom, k equals 1, that tells me that k is my indice and that I'm starting at 1. And where to end, the number above the sigma. That n, I'm going to go all the way up until whatever n is. Right now we're just saying n because we don't know. If you're told to calculate it, you'll be given an n. So we can write that k equals 1 says the index k starts at k equals 1. And this n on the top says that the index k ends when k equals n. Right, this big sigma, that's our summation symbol. You might have also seen one that's a giant pi. It's for products. So summation starts with an S, so it's a giant sigma. This a sub k is a formula for the kth term. Sometimes you're given it, sometimes you have to find it, depending on the question, right? So we're asked to rewrite in sigma notation, right? So I'm given this sum, 1 squared plus 2 squared, all the way up to 11 squared, and I need to write it in sigma notation. So I'm going to draw my sigma first, and we can do k, we could also do I, it's kind of whatever you want. Sometimes people do j, so we'll be consistent, we'll do k equals 1. And then I like to make my formula. So I like to kind of start with k, the bottom, go to the middle, and then end to the top. Some people do whatever is best for them. They make their formula, then they choose what k is, and then they pick the last number, the top number. So if I'm choosing k equals 1, I see that every term is just squared, and it's every next integer. So I don't need to change it. So I'm just going to call this k squared. And I go up 1, 2, 3, blah, 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 to 11. So that means this top number is going to be 11. All right, so the next one, I'm not given any numbers, but I can still write it in summation. So let's choose something else. Let's choose I. I equals to 1, right? So I know I'm going to plug into my function f. I don't know what that is, but I'm going to plug in f1, f2, f3. So I'm going every integer, right? That's good. My index can only go every integer. So we can do f of I. So that means my first term, I'll plug in 1, and then I'll plug in 2, and I'll plug in 3, all the way up until I get to 100. And that's how I got that top little number. K doesn't always need to start at 1. It can start wherever you want to, but it will change everything else. So that's why I kind of like to choose what k is first. So then I know how to write my equation with that a of k, and then I know what that top number needs to be. So we're going to express 1 plus 3 plus 5 plus 7 plus 9 in sigma notations in different ways. So first thing that we kind of need to make a note is that even numbers I can write as like 2k. Odd numbers, it's going to be 2k plus an odd number. Okay? Even numbers, you can do 2k plus an even number. In this case, 0 is an even number. Don't argue with me about that. And so that's kind of the basis of what we're going on. So I have all these odd numbers, so I'm going to do 2k plus or minus some odd number. Okay? So if I start with my sigma, and let's let k equal, let's let k equal 1 right now, and then we'll go, no, let's choose k equals 0. Sometimes 0 is a really good one to choose as well. So I know I need 2k because they're all numbers, and then I needed plus or minus a number. So what I like to do is I know that I'm going to plug in k equals 0 first. So I know that 2 times 0 plus something needs to equal 1. Well, 0 plus x equals 1, so then x equals 1. So I can do 2x plus 1, and I'm starting at 0, and I'm using 5 terms. So it means this one's going to be 0, k equals 1, k equals 2, 3, and 4. There's 5 terms, but k has to go all the way up to 4. Okay? If I wanted to keep with what we're doing and do k equals 1, I would have to do 2k, and then I want that first term when k equals 1 to equal 1. So, well, that's 2 plus x equals 1. So x equals negative 1. So this is going to be minus 1. And then, since this is k equals 1, this is 1, 2, 3, 4, and 5. So my top number is 5. All right? You can continue on and try it when k equals 3, k equals negative 3, and so on. But you can kind of follow the same process here of choosing what k is starting with and kind of knowing what you know about numbers. Like I know evens 2k plus an even number minus an even number. Odd numbers are 2k plus an odd number minus an odd number, and so on. Okay? So there are some algebraic rules that come with some summations. So the sum rule, it kind of seems a little like, well, duh, summations. This is saying like A1 plus A plus B1 plus A2 plus B2. I can rearrange those and make 2 different summations. So I can add all the A's together from 1 to n. Then I can add all these B's. Oops. Together, 1 to n. Similar with the difference rule. If I have the sum of AK minus BK, I can add up all of the A's from 1 to n. And then I could subtract, since all of B's are being subtracted from the A, I can subtract once I add up all of the B's. That one actually comes from the coefficient rule, meaning that what we kind of saw last section where I had everything multiplied by delta k, and then I can just pull, not delta k, delta x. I can just pull that delta x right out and then add everybody together. The constant rule is actually pretty interesting. If I'm adding a constant in times, 1 plus 1 plus 1 plus 1 10 times, well, that's 10 times 1. So this is just going to be n times c. So So the summation kind of just goes away. So notice that I'm multiplying this top number right here times c, and c has nothing to do with k. All right. So let's do a few examples. So we're just going to rewrite these 4 expressions using the 4 algebraic rules we just went over. So we're going to yawn. Sorry, water break. The sum from 1 to n of 3k minus k squared. So difference rule means I can split up this term and this term, and I can pull out that 3 and that negative. So I can rewrite this as 3 times the summation of k equals 1 to n of k minus the summation from k to 1 to n. That's not changing at all. That doesn't ever change with these algebraic rules. Minus k squared. That squared is only to the k, so sometimes you'll see it like this so that you know that I'm squaring that term and then adding it. Because it's different to add those terms together and then square them. So different. All right, so the next one is if I just have a negative a to the k from 1 to n, well, I can pull that negative out like a negative 1 and then use the coefficient rule, oops, and just make the whole summation negative. So that's why there's not like a difference quotient, not quotient, there's a difference quotient. Like there's only summation, there's only summing, because if I want to subtract all these things, I could just make a negative out front. All right, so then k equals 1 to 3 of k plus 4. This one we actually are going to find the solution to, since it does have a finite number up top, or it gives me like an actual number. So we're going to split these up from k equals 1 to, not n, to 3 plus the sum of k equals 1 to 3 of 4. Well, we know that this is just going to be 1 plus 2 plus 3 plus, well, 4 times, 4 just has nothing to do with k. So it's a constant, so we're going to use the constant rule. So that's just going to be 3 times 4. What is that? 6 plus 12? 18? Yeah. And that one equals 18. Fun little summation right there. So even though number 4 has an n, you're like, oh, that's not a constant. It actually is a constant, because just like we saw on 3, if I have n equals 3, that'll be like 1/3 plus 1/3 plus 1/3 added 3 times. So this is actually going to equal n times 1 over n, which actually equals 1. Pretty cool, right? So I'm not going to show you the whole proof of how to get these fun formulas to know, but I would know them. So we have the first n integers, first n squares, first n cubes. All right, so the first n integers, that sum, so you're just adding k, the summation of k from 1 to n, is going to be n plus 1 over 2. This is actually a super interesting way to find the sum of all of the first 100 integers. I forget who, there was some mathematician that figured out how to do it. It's really cool. So the summation goes away, and we can just multiply n times n plus 1 divided by 2, and that'll give us the answer. The first n squares is going to give us n plus 1, n plus 2. Oh wait, no, not n plus 2. I read that wrong. 2n minus 1 over 6. And then the first n cubes we can write as n plus 1 over 2, that whole quantity squared. So I am just kind of telling you these things. You have to take me as face value. But know these 3 formulas. They're going to be really important. So let's do a few examples of how to express following in sigma notation. So we're not really going to use the formulas to know right now. We're going to use those in a hot second. But these are probably my favorite, like, 2 examples to use of where you're given a sum and you're asked to write it in sigma notation. So the first one is problem 13 for this chapter. So you're given that 1/2 plus 1/4 plus 1/8 plus 1/16. All right. So I just kind of like to write my sigma next to it and then kind of do work below it. Okay. So I have my sigma and I need to choose where I want to start. So let's start with I want to start with k equals 1. The next one will do k equals 0. So then I know everything is 1 over something. So I'm going to have 1 divided by, I see the first one's 2, the next one's 1/4, 1/8, 1/16. So let's do 1 over 2 times k. Since I'm starting at 1, I'm going to have 1, 2, 3, and 4. So I'll stop at 4. And I'll see that I'll get 1/2 plus 1/4 plus 1/6. 2 times 3. Well, that's not it. All right, scratch that off. How can I make 2 go from 2, 4, 8, 16? Well, those are the powers of 2. So I can raise 2 to the k. Right, so then I'll get 2 to the first power, which is 1 over 2 to the first power, which is 1/2. 1 over 2 squared, which is 1/4. 1 over 2 cubed, 1/8. And 1 over 2 to the 4th, which is 1/16. All right, pretty cool. So the next one, now we have kind of 2 things that we need to work on. Making each term and then making each even term, so, or each other term negative, starting with the first one being positive. So let's make this one I equals 0. So I have 1, 2, 1, 1/2, 1/3, 1/4, 1/5. So I know I'm gonna have like 1 over I and then I'm gonna have something else involved. I can move that over a little bit. So I'm committed to, not over 1 over I because I started at 0. This needs to be 1 over I plus 1. So that if I plug in 0, I'll get 1 over 1. And then I'll plug in 1, and I'll get 1 over 2. I need to figure out how to make it negative. 2, 3, and 4. So again, I'm going up to 4. But I'm starting at 0. So now I need to figure out how to make this every term negative. So when I plug in I equals 1 and I equals 3, they need to be negative. So we're going to use the property that -1 to an odd power is -1. And that -1 to an even power is 1. In this case, anything to the 0 is also 1. So kind of making 0 and also an even number. So if I multiply this by -1 and I raise it to I, well, that's going to give me, once I put, for the first time, I'll get a positive 1. And then I put in when I equals 1, I'll get 1 over 2 times negative 1. Well, that gives me a negative 1/2. That's exactly what I wanted. And so on. I could have also done this where I equals 1 up to 5. So that I had 1 over I. And I could have done negative 1 to the I plus 1. And stuff like that. And so on. All right? So if those were a little confusing, take a step back. Read through kind of the stuff we did but above, because it's going to get real serious when we talk about limits of finite sums. Alrighty. So limits of finite sums. We talked about in 5.1 what we about approximating area under the curve using sums. So we use sigma notation to help with the finite sum approximation. And I think we talked about right at the end how if we keep adding more subintervals, they're going to keep getting skinny and skinnier. We saw that when we had like n equals 16. So if the width of the subintervals approaches 0, so delta x, the number of subintervals is going to approach infinity. So I wrote that as the limit as n approaches infinity of delta x, right? Remember, we can write delta x as b minus a over n. Well, as n goes to infinity, we know from a few chapters ago that that's going to approach 0. So that's kind of what we're saying. So we're going to find the limit of the lower sum of y equals 1 minus x squared. All right, so first we need to split 0 to 1 into n subintervals, in even subintervals. So delta x is going to be 1 minus 0 divided by n, which is just 1 over n. And that gives us each interval. So our first one's going to be from 0 to n, 1 over n, 1 over n to 2 over n, and so on. And then our final interval is going to be n minus 1 over n to n over n, and that's just equal to 1. So since 1 minus x is decreasing, which we saw last section on 0 to 1, the lesser endpoint will always be the right endpoint. Right, so if I'm like going down like this, I'm decreasing. This endpoint, this right endpoint is always going to be the lower one. So that's why we're going to use right endpoints here. So the height of the kth rectangle, we're going to plug that in to our function y minus 1 minus x squared. I'm using k here to kind of work with that sum. So we have 1 minus, and wherever there's an x, I'm going to put k minus n. So, or sorry, k over n. And then I can simplify that to 1 minus k squared over n squared. Okay? So, then the sum will be all of those guys added together, right? So like 1 over n is my delta x, excuse me. And then I'm adding up each right endpoint right there. So I'm going to plug in for f of k over n. Then I'm going to distribute that 1 over n to each term and also make that middle guy look like that. So then this is a little simplification, and distribution will give me 1 over n minus k squared. That'll be n squared times n, so that's n cubed. Using some of those algebraic laws, we know, oh, I don't want that. Right, we saw that 1 over n. That summation is just going to be n times 1 over n minus the sum of k equals 1 to n k squared over n cubed. So this equal 1 minus this 1 over n cubed can come out. Well, now I'm adding up the first n squares in this guy. So I can scroll back up to, bless you, my cat sneezed. Where is it? We're going to use this. So scroll back down. 1's going to stay there. 1 over n cubed times n plus, nope, n plus 1, 2n minus 1 over 6. And now I'm going to simplify and distribute that n cubed to the bottom. So basically expanding the numerator. So I'll get 1 minus 2n cubed plus 3n squared plus n over 6n cubed. All right, so now I have something that I can plug in for any number of n and get the lower sum approximation of the area, right? So, right, we care about when the limit, where'd it go, of n goes to infinity. So now we're going to take the limit of this and using some handy-dandy limit rules that we learned from past chapters, I'll get that this is 1 minus 2/6, which is the same as 1/3. So 1 minus 1/3 will give me 2/3. And we'll learn tomorrow how to make sure that is the absolute answer. It is the answer, but this is like the old-timey way of doing it before we know some fun other tools. All right? So that's kind of what we mean when we're talking about limit of finite sums, is kind of doing something like this. All right? So then we're going to briefly just talk about Riemann sums. We've kind of already been doing Riemann sums. That's what these like rectangles are. Basically, all the different discussions, different sums that we've discussed in 5.1 are Riemann sums, so like upper, lower, left, right, middle point. Riemann sums is kind of like a really broad use for like finite approximations, and sometimes they're also, they don't have even subintervals, so, which is like really weird. Also, I wrote sides instead of size. Okay. So we can denote the different widths of each kth subinterval as delta x sub k. So we call like S of p the Riemann sum, where S of p equals the sum of all that like function value over that sum interval. Right, remember C of k was just some value in that subinterval, and delta x of k is that certain subinterval's width. So we only really work with Riemann sums with even subintervals, so we can make a more general, or not general, I guess a more specific to our use formula. So let's let S of n denote the Riemann sum within even subintervals. And when I say even, I don't mean like 2, 4, 6, 8, mn. I mean like equal size. All right? Because that's the only ones we're going to work with. So, and we're going to only work over a to b. So we write S of n is equal to the sum of f of a plus k b minus a over n times b minus a over n as k goes from 1 to n. You're like, what? This is so crazy. I don't understand this. Well, remember b minus a over n is just delta x. So we can just rewrite this as f of a plus k times delta x times delta x. And the reason Riemann sums are kind of written like this is because you know that you're going every delta x. So say when we moved midpoint rule, if I was at like halfway between one interval and each interval is the same, I'm still moving that interval's length or width, not length, width. So this is just a different way of writing like f of ck can equal f of a plus k delta x. If I'm going 3 intervals over, I know I need to add wherever I started from and then go 3 times that to get to my next value. I hope that makes sense. Riemann sums are really interesting. It's a big mathematical law, but it's a little over what we need to talk about in this course. So I'm just going to leave it at that. And I will see you guys tomorrow. Goodbye.